Okay, so our question here is this. We have a two-body kinematics freefall question with two stages and an initial separation. Here it goes. A helium balloon begins to descend from a height of 30 meters at a constant velocity of 2.3 meters per second. 5 seconds later, a rock is thrown upward from a height of 1.8 meters with an initial velocity of 2.5 meters per second. At what height does the rock hit the balloon? The key thing to understand here is that the balloon is not in free fall. It's falling at a constant velocity. So air pressure is pushing up while gravity pushes down. The two balance. It falls at a steady 2.3 meters per second. The rock, however, is in free fall, meaning as soon as it leaves the person throwing its hand, it's accelerating downwards at 9.8 meters per second squared, and it goes up with an initial velocity of 25 meters per second, starting from an initial height of 1.8 meters. So to solve this problem, I'm going to split it into two stages. The first stage is the first 5 seconds, because 5 seconds after the balloon starts to fall, the rock is thrown. So let's figure out where the balloon is going to be at the end of those 5 seconds. So stage 1, the balloon has an initial position of 30 meters. So I'm going to consider up to be positive throughout this question. It has a displacement of velocity times time, because it's constant velocity, so minus 2.3 meters per second times 5 seconds. So that's minus 11.5 meters. So the final position is equal to the initial position plus the displacement, 30 meters minus 11.5, making it 18.5 meters. So at the end of stage 1, which is the first 5 seconds, the balloon is 18.5 meters above the ground. We're now on to stage 2. So stage 2 starts at the end of the first 5-second period. So in stage 2 we have a balloon and we have a rock. The balloon has an initial position of 18.5 meters. We determined that in stage 1. So the final position of stage 1 is the initial position of stage 2. The rock has an initial position of 1.8 meters. The displacement of the balloon, because it has a constant velocity, is still negative 2.3 delta t. That is, it's its constant velocity times time. The rock, however, is in free fall, so its displacement is equal to its initial velocity, which is 25 meters per second times time, plus half acceleration times time squared, which is in this case plus half of negative 9.8 delta t squared. And I'm just going to go ahead and simplify that. Okay, let me move this over so you can see it better. Okay, so stage 2, the balloon starts out 18 meters high, the rock starts out 1.8 meters high. The balloon's motion, so its change in position or displacement, is governed by this equation. Displacement of the rock, which is in free fall, is governed by that equation. Now the key to setting up these problems is to understand that your displacement, your delta d, is equal to the final position minus the initial position. So that means the final position of the balloon, d2, minus its initial position is delta d. So the final position of the balloon is the initial position plus delta d, which means the final position of the balloon is 18.5 meters minus 2.3 delta t. Likewise, for the rock, the final position of the rock is d1 plus delta d, so it's 1.8 meters plus 25 delta t squared minus 4.9 delta t squared. I copied that wrong, that's just delta t. 1.8 meters plus 25 delta t minus 4.9 delta t squared. What we want to do is find out where the rock meets the balloon. So we want the final position for the balloon to be equal to the final position for the rock. So I'm going to make this side of the equation that describes the final position of the balloon equal to this side of the equation that governs the final position of the rock. And when those two are equal to each other, we solve for delta t, and that's going to tell you the time where the rock meets the balloon. So we'll just copy those out, and we have 1.8 minus 2.3 delta t equal to, oh sorry, that's 18.5. 18.5 minus 2.3 delta t is equal to 1.8 plus 25 delta t minus 4.9 delta t squared. So I've just made this equal to that. Now rearranging things, we'll bring all numbers and letters to one side and just put 0 on the other. And then we can send this to the quadratic formula.
Excuse me for the interruption. Could I have all staff please complete your attendance? Thank you.
And then running the quadratic formula into your calculator, you're going to arrive at delta t is equal to 4.87 seconds, or 0.6996 seconds. Now remember, we should get two answers from this scenario, because initially we have a balloon that's falling slowly, and we have a rock that's been thrown upward quickly. So a little while later, the balloon has fallen a bit, and the rock meets the balloon. The math governing its motion, however, doesn't account for a collision. So it will later have the balloon falling a bit further with the rock up here, and then the rock falls back down under gravity, accelerating at 9.8 meters per second squared, where it eventually hits the balloon for a second time. So our two solutions from the quadratic, this one tells us the time where the rock initially hits the balloon, and this one tells us the time that the rock hits the balloon for a second time. Given the context of this question, we're interested in this solution. Now, we weren't asked the time though, we were asked the location. So the final position of the balloon and the rock, I could take either D2 for the balloon or D2 for the rock. Plug in that time, and they're both going to give me the same answer. This one looks simpler, so I'm going to use this one. So the final position is equal to 18.5 meters minus 2.3 times 0.6996, which is 16.9. So the rock is going to hit the balloon at 16.9 meters above the ground.